Ever since first having seen a piano and learning about scales, I've been wondering why there are 8 tones in an octave and why the black keys on a piano are not evenly spaced. Okay, so you can simply learn things by heart and accept cultural facts without questioning them, which is what we humans usually do, don't ask, accept and repeat. But why? Why? I can sort of accept a specific amount of tones, but why a few tones do have to be placed a semitone apart and the others a whole tone is not immediately intuitive at all. So what could be the reason? Let's start with what a tone is. Essentially, I have a swinging medium, such as a string, and when I let it swing, standing waves with 1, 2, 3, etc. peaks will emerge, just as if I swung a rope. Waves with non-integer amounts of peaks, say 2.7, will be present as well, but they will dissipate rather quickly because they're much less stable. Plus, reality is always messy, which is, by the way, why the probability of us living in a tightly controlled simulation is minuscule. In any case, strings will usually swing with several tones at once. They are fittingly called overtones and contribute to the timbre of a tone, the very reason for a piano sounding different to a guitar, say. The more or less pure integer waves are called the Harmonic Series. So the different tones one can produce by making, for instance, the column of air within a natural trumpet, without bells and whistles, vibrate. Naturally, because the trumpet has a concrete length, the dominant waves will be the static ones starting and ending at the start or at the end of the instrument's body, respectively. If we were now to depict these tones on a piano keyboard, they'd form a pleasing progression. So the second tone is as if half the string of the original tone swung, the third one as if a third of it, etc. The ratios between each two adjacent natural wavelengths would thus be 1 to 2, 2 to 3, 3 to 4, and so on. Now, if we were to count the actual white keys on a piano between any two adjacent tones of this emerging progression, we'd arrive at counts of 8, 5, 4, 3, and lesser 3, because there are 2 black keys in the first white 3 and 1 black key in the last white 3, respectively. This is also why these intervals are therefore called octave, 5th, 4th, major 3rd, and minor 3rd. But that's really just a piano-related observation. It doesn't answer the initial fundamental question why there are 8 tones in an octave and why some white piano keys don't have black ones between them. Well, let's build a scale. A quote-unquote pure Pythagorean one. Shout out to Pythagoras, the ancient Greek bloke. Of our aforementioned ratios, the 1 to 1 one is trivial, so the 1 to 2 one is the next one in line and indeed the most fundamental one, i.e. the octave. Indeed, if we let a string swing together with half the length of the original string, or indeed double the frequency, the 2 tones sound highly harmonious. Many people perceive them as essentially the same note, so in Western music, here in the so-called Helmholtz notation, they might be denoted by an upper and lowercase c, respectively. Why that's a C and we don't usually start the major scale at the A is a different question entirely, and I might tackle it if I have time in a future video. And of course there are many more other questions that we cannot really deal with today. Because of this near equivalence of tones any number of octaves apart, we can have or double tones outside the interval between these first 2 tones so as to construct a scale in between and still preserve the fundamental properties of these tones. Now the next fundamental ratio after 1 to 1 and 1 to 2 is 1 to 3. But 1/3 is beyond the border of 1/2. Since we want to stick with the traditional order of higher tones of frequencies being to the right of lower ones, the wavelengths decrease towards the right. But no worries, we'll just double the 1/3 and thus bring it right back into the fold between 1 and 1/2. The ratio between the original 1 and the freshly added tone is hence 2/3. Now what if we were to create an antipode to the 2/3? That is, if we were to divide 1 by 2/3 and not multiply by it, well, we'd arrive at 3/2. But since, again, 3/2 is beyond 1, we halve it and obtain 3/4. I've rendered the distances between the points on the axis somewhat normalized and abstracted, by the way, since we'd otherwise arrive at the harmonic curve we saw earlier on, and that would somewhat obfuscate the scale. We've now arrived at 1, 3/4, 2/3, and 1/2. The original tone, and tones a perfect 4th, 5th, as well as an octave apart. However, we still don't see why these should be called 4th, 5th, and octave. But we can simply observe that the 2 newest tones we've added to our scale have a ratio of 8 to 9, 8/9. That is the ratio between 2/3 and 3/4. This will ring a bell, or rather a string, if you will, in a minute. Now, since the 2/3 are a very handy interval and sound very, very harmonious together with the original tone, we'll just keep multiplying by 2/3 and creating new tones that sound equally harmonious with the previous ones. And of course, applying the trick of halving or doubling at will in case we land beyond the confines of the interval between 1 and 1/2. We don't have to scrutinize the arithmetic. You can verify the results on your own. We quite simply end up with the numbers rendered red on the screen. And if we were now to fill the gaps of our emerging scale and compute the ratios between any two adjacent tones, we see that these ratios indeed mostly equal 8/9, with the exception of two of them, exhibiting a rather more complicated ratio. However, after having arrived at these 8 tones now, we've filled our scale in a way that there are no gaps larger than 8/9. You remember the exact interval ratio between the initial 2/3 and 3/4, our first whole tone step, if you will. Of course, you might continue by 2/3ing well ad infinitum, but we've now neatly filled our space with 8/9, since a sixth 8/9 would lie beyond 1/2. And therefore these 5 tones lying 8/9 apart, as well as the 3 supplemental original ones, namely the 1, the 1/2 and the 3/4, they thus quite, well not completely, but quite naturally form the 8 tones of an octave. In addition, we must observe that it will never be possible to arrive at either 1/2 or 3/4 by simply continuing to multiply by 2/3 and double or halve at will, because their denominators, those would be the parts below the division line, will always be coprime, meaning divisible only by 2 on the one hand and featuring 3's on the other, and 3 is simply not divisible by 2, nor is any power of 3. Which is why there are smaller gaps, semitones, just before the 3/4 and the 1/2 point, tones 4 and 8 in our freshly baked scale. So if you think about it, the mathematical structure of this very world therefore prohibits us to ever devise a truly perfect scale. Isn't that quite something to ponder? But what we have been able to see and grasp now is why there are 8 convenient tones in an octave, and why, as we saw last, there is a semitone spacing between the 3rd and the 4th, as well as between the 7th and the 8th tone, if we just do what we did, and that was multiplying by 2/3, continuing in the vein of fifths, and that's essentially what the so-called major scale is all about. Now, in practice, one would very much like to use tones across several octaves, while still preserving melodically mellifluous intervals between tones, even spanning several octaves. Different ways of tuning have hence evolved to bridge this gap. The Pythagorean scale we just developed together works well within 1 octave, but even the tone just above 1/2, so 8/9 to its right, would not be 2/3 away from the original 2/3, for all the reasons we just saw a minute ago, the coprimeness of 2 and 3, whereas it should be if we were willing to preserve harmonic coherence across octaves. One manner of somewhat mitigating risks is the so-called just temperament, where some tone intervals huddle closer together and some others are spaced farther apart, but all ratios are much simpler than the complex 243/256th semitone step we arrived at before. Our ears, it turns out, perceive frequencies of a similar ratio as melodic, whereas combinations of adjacent tones are usually perceived as very tense, at least in the Western music tradition. Similar frequency ratios essentially means we are much more at ease when hearing a pair or sequence of tones whose frequency ratio is sufficiently simple, mathematically speaking. We thus have an oral predilection for smaller and more beautiful numbers, it seems. However, if the deviation is minuscule enough, our ears don't care that much, which brings us to powers of the 12th root of 1/2. How so? Well, let's add semitones across the board, hence also between any 2 tones just 8/9 apart, firstly, and there were 5 of these. And secondly, let's make sure all resulting 12 of them are equidistant, which means timesing the semitone interval with itself 12 times must equal 1/2. And this semitone step, i.e. the 12th root of 1/2, is apparently not too far away from 15/16, and its square, that will be a whole tone interval, isn't too dissimilar to 8/9. So it's not perfect, because only the octave will ever be perfect in the system, but it'll apparently do, especially since we can now juggle all tones and build scales up and down and across. And that's why most pianos are equally tempered and have conquered the world in a musical sense. I've left a few interesting links to videos that are music theory related in the description, and that's that then. Cheers!